look at, we look at solubility. That's one of the important characteristics for metathesis reactions, but there are other factors there too. We're going to look at those other factors when we start talking about the reactions specifically. Right now we're still dealing with chemical compounds and formulas, but we also want to look at acid-base properties for these. And so one thing we'll look at is if there are acid-base properties. And the acid-base properties, I do have a nice chart that I'd like to post here. It's not in your book, but let me see. Still, I'm having a computer issue. But if you turn your head and take a look, you see that chart there in the back? That's a relative strength of acids and bases there. And so what we want to do is, that's just a lot of data. We want to get familiar with that. Like, for example, what is the strongest acid on that chart? Yeah, what is that again? HClO4, which is called hydrochloric acid? Perchloric acid. The strongest acid on that chart is perchloric acid. What's the next acid? Let's name them. Hydroiodic acid. Sorry, I put this on the projector. I don't know. Hydroiodic, followed by hydrobromic, followed by hydrochloric, followed by nitric, followed by, no, we don't call it dihydrogen sulfate. Even if we name these as ionic, we just call it hydrogen sulfate. We wouldn't use the di. The di is strictly for binary. Binary means what? Two. Binary. This is not binary. This is more than two elements, so we never use that. We have to use different nomenclature. And so this one, we call it hydrogen sulfate, or it's an acid, so we're going to name it the acid name, which is, we wouldn't call it hydrogen sulfate, we'd call it sulfuric acid. And then what's below sulfuric acid? Sulfuric acid is a polyatomic ion that I didn't talk about. It's H3O+. Yeah, H3O+ is called hydronium ion. It's one I didn't talk about because H3O+ does not occur in compounds. H3O+ occurs in liquids, you know. And so this is the hydronium ion. Okay, so above hydronium, how many acids did you have? Count them. 6. Okay, above hydronium, we're going to have the 7 common strong acids. So one acid's missing. The one acid that's missing off this chart, that's on our chart, the one I'm going to hand out eventually. Actually, I should have printed it out. Is HClO3. HClO3 is called hydrochloric. Is not HCl is called hydrochloric acid. Yeah, just chloric acid. And so we have the 6 on the chart plus this one, which is the 7. Typically, people memorize these. Below hydronium, we have what are called the weak acids. Should you memorize the weak acids? No. You don't bother. There are too many weak acids to memorize, right? And so what we do is we memorize the strong acids and say, if it's not a strong acid, then it must be a weak acid. Most of the time, you'll be correct. And so when we look at a chart like this,
do we need to remember the order of strength of the acid?
No. you don't have to remember the order of strength. You'll always have the chart. Otherwise, it's too much to remember. There's certain patterns in reactivity. You can kind of figure it out, but that's later on. Initially, what we want to do is we just want to get familiar with the chart. When we get familiar with the chart, one of the things that people don't do is they don't read every entry on the chart. And so in order to start finding these patterns, we have to at least read every entry on the chart. And we should be able to name every entry on the chart. Can we name everything on this chart? I don't know. Let's try. Okay, below hydronium, which is a weird one, is this one. We don't have to name it because they give you the name there. You see the name? Oxalic acid. What's the formula for oxalic acid? Yeah, Cu. That's the name. But what is the normal formula for oxalic acid? H2C2O4. H2C2O4, oxalic acid. Below oxalic acid is what acid? What is H2SO3 called? Sulfate is, what is the formula for sulfate? Let's go off that first. Sulfate is SO4. That is SO3, so it's not sulfate, it would be sulfite. And if we have an ite, what do? We drop the ite and call it ous acid. So that's called sulfurous acid. H2SO3, sulfurous acid. Sulfurous acid, what's going on with the parentheses? Do you see that parentheses business next to it? Parentheses SO2 plus H2O. Do you know what that means? That means that sulfurous acid is inherently unstable and it decomposes into SO2. What is SO2 called? Ozzy, you got this one. SO2 is called? Okay, sorry. Now you can use your prefix.
Oh, that's fine.
All right, sulfur dioxide, like carbon dioxide. So it's binary, right? Two elements. They consist of all nonmetals, and so sulfur dioxide and water, or dihydrogen monoxide. But we wouldn't call it. We could call it dihydrogen monoxide because it's also binary nonmetal. But H2SO3 is what we call ternary. So we wouldn't use the next one's also ternary, so we wouldn't use the prefixes there. What would we call the next one? The next one has a charge on it. Is that sulfate or sulfite? Sulfate, and it has an H on it, so we call it hydrogen sulfate. Two words, hydrogen, then sulfate, or AKA bi with a B, bisulfate. It's bisulfate. Now look at the position. I'm sorry. The charge is -1. No, you just say bisulfate ion. Yeah, then everybody's supposed to know the charge. They have to memorize.
You have to say ion.
You have to say ion. Well, if you say bisulfate, it's pretty much an ion. You don't really need. Now look how strong. Is bisulfate a pretty strong acid? You know, it is. Bisulfate's pretty decent strength. It's weaker than sulfurous acid, but stronger than the one below it. What's below it? The one below is H3PO4. H3PO4 is phosphoric or phosphoric. Phosphoric. The one below the phosphoric acid is a pretty decent strength acid, and bisulfate's stronger. This is rank in strength. Again, you don't need to know the order, but what you want to do is you want to go through the chart and then is called hexa-aqua iron 3 ion. And hexa-aqua iron 3 ion is discussed in Chem 1B, not even in Chem 1A. We talk about that, but that's a pretty decent acid. You know what it is iron 3. Did you know some ions are pretty acidic? So iron 3, any iron 3 salt dissolved in water is pretty acidic. But you should know what's below that one. HF, that should be an easy one. What is HF? Yeah, HF is hydrofluoric acid. But you know, HF is kind of the odd one out. Do you see the pattern already? Why is it the odd one out, HF? What about the other members of the family? The other members of the family, iodide, bromide, chloride, they're all ides. Yeah, fluoride is 9 too. These are all ides. But look, take a look at that chart again. I know it's the first time. The first time you don't pick these things up. The only time you pick these things up is after looking at it multiple times. But one of the things you notice is that what's number 2 in spring? HI, powerful acid. HBr, powerful acid. HCl, powerful acid. HF, not powerful. HF, why is HF the odd one? That has, yeah, it has to do with the size and other things. But even though HF we consider weak acid, the other members of the family are considered strong acid. Even though HF is considered weak acid, HF is one of the most dangerous acids. It's one of the most dangerous acids out there, not because of its acid properties. If you look at just its acid properties, people say it's a weak acid. Hey, it's weaker than phosphoric acid, you know? Actually, they're trying to ban HF at the refinery over here, Orange Refinery. Did you know that? They use HF in the processing over there, in the refining process. A lot of people are against it because HF is kind of a dangerous chemical. It's a dangerous chemical not because of its acid properties. When you spill some HF on you, it doesn't really burn. Like if you spill perchloric or hydrochloric, it burns. You know, it causes like first degree burn, second degree burn. HF really doesn't burn that much. But what happens is HF, you know, HF sinks through, or what they call permeates, or diffuses through your flesh and then hits the bone. When HF hits the bone, then you're in big trouble because a metathesis reaction occurs. The metathesis reaction occurs as fluoride ends up swapping places with hydroxide in your bone. Apparently that precipitation of calcium fluoride is excruciatingly painful. You can't wash it off. You know, if you try to wash it off, it's already penetrated through your flesh. Yeah, so the people who work with HF, people in the electronics industry, a lot of them work with HF for etching semiconductor. They have injection kits, you know. They have injection kits filled with calcium glutamate or something like that. You're supposed to inject yourself with calcium. And the calcium ion and fluoride like each other. Calcium fluoride precipitates, so it's better than precipitating on your bone. Something like that. So HF, even though it's a weak acid, it's got some nasty metathesis properties. Worry about what's below HF? HNO2, which is called nitrous acid. This is nitrite. So nitrous. Actually, you can see the anion to the right of it. Can you see that? Yeah. Below nitrous acid is. Yeah, it's a pass. Chromium ion and water. Iron and water is pretty acidic. Chromium ions too are pretty acidic. Chromium 300. Below that, something called benzoic acid. You don't have to know that. You don't know the organic, you don't have to know that. The one, okay, now we go to the other side. Do you recognize that? On the other side there? Yeah. salts are fairly acidic. They attach to water. Below the aluminum thing, the pass, we go to H2CO3, which is called H2CO3 is called carbonic acid. Carbonic acid decomposes into carbon dioxide and water. So there are two acids that are inherently unstable. What are they? Carbonic acid and sulfuric acid. Sulfuric is stable. Okay, below that is H2S. We have two names for H2S. Most people call it by the ionic name, not the acid name. If you name that as an ionic compound, what would it be? H2S. Hydrogen sulfide. So that would be hydrogen sulfide, the raw negative gas. Or, as an acid, what would you call it? Yeah, you call it hydrosulfuric acid. Okay, below that is an acid anion, which we call dihydrogen phosphate. Below that, hydrogen sulfide, hydrogen sulfide ion, or AKA bisulfite. Below that is boric acid, correct? Next, ammonium. Ammonium is a pretty weak acid, but it's an acid. You can donate an H+. When it donates an H+, we form ammonia. Below ammonium is HCO3 minus, which is called what? Hydrogen carbonate. Another name for hydrogen carbonate is bicarbonate. Okay, below that is, most people name this using the ionic rules rather than the acid rules. If you name that as an ionic compound, what would be H2O2? Hydrogen peroxide. As a acid, what would you call it? Close. What did you say, hydroxylic acid?
Yeah.
No. What's the anion mean? Peroxide. So it would be hydro peroxic acid, hydroperoxic acid. Followed by, yeah, we call this monohydrogen phosphate. This is the one above it, which is a little stronger, which is dihydrogen phosphate. Followed by hydrosulfuric acid is H2S. That would be the hydrogen sulfide ion. Here we definitely need ion, otherwise people might confuse it with H2S. Below that is water. Now, can water be an acid? Yes, actually water can be an acid or base. Now it's weak, for sure it's weak.
Is water considered neutral?
It's considered neutral because it's considered neutral because it can react as easily as an acid as a base, as it is a base. But it can act as an acid or it can act as a base. Pure water is neutral. It depends on what you mix it with, and that will dictate how water behaves. Okay, below that is hydroxide. Now this is weird because hydroxide is considered a powerful base acid anyway, so it would even work. All right, now this chart is very convenient because we have a conjugate relationship. Have you ever heard of a conjugate relationship? A conjugate relationship means that we don't have two separate charts. So for example, what it means, HClO4 is the most powerful acid on that chart. You know what that means? That means HClO4 loves to donate an H+. That means ClO4 minus doesn't really care. ClO4 minus, what's ClO4 minus called again? Perchlorate. So perchlorate really doesn't care if it loses the H+. Oh. And so what we got going here is this. Basically, if this is very strong acid, then its conjugate is very weak base. Likewise, let's go to some of the weaker ones. H2O, this is a very weak acid. And therefore its conjugate will be a very strong base. So for example, hydroxide here, when hydroxide really wants a H+, it doesn't really want to let it go. So water losing the H+, or in the acid-base reaction, makes a very strong base. This is the conjugate relationship here. And so what we should do is we should name the bases. What's the strongest base on the chart? The strongest base on the chart would be at the bottom right. I know it's hard to see. Let me see if I can get this going again. I'm going to restart this computer. The strongest base on the chart is at the bottom right here. It's just this chart. It's called NH2 minus. NH2 minus, since it's the strongest, we might as well know its name. The name of this is called amide or amide ion. And it's a very powerful base. So what makes a powerful base? A powerful base wants H+. And so amide really wants H+. Above amide is this one. This one, O2 minus, is called oxide. And then above oxide is OH minus, which is called hydroxide. And then we have the anions that go up. So when we're looking at that chart here, it's hard to see. But we can go up the chart. So as we go up the chart, it's just the anions here. Now, all these are bases. These are bases, like for example, amide is a very powerful base because it really wants that. And so what the amide can do is, if there's amide around and there's water, normally we don't think of water as being a very good acid. In fact, water we normally think as being quite a weak acid, if that. But amide's so powerful, what amide does is it comes over here and strips that hydrogen right off water. And so it forms NH3, and then when it strips the hydrogen off water, we form hydroxide. And so what we want to do is we just want to familiarize ourselves with some of the common acids and bases and a little bit about the strength of those acids and bases. Okay, after, so basically, for acid-base properties, we consult a chart. we don't memorize that chart except for the 7 strong acids. Do you remember what the 7 strong acids are? Perchloric, chloric, hydroidic, hydrobromic, hydrochloric, sulfuric, nitric. Yeah, we memorize those. We remember the conjugate relationship. This is the conjugate relationship. And so there's no separate table. You know, the acids and bases are in the same table. Okay, then we do one more thing we're going to look at. Yeah, I should have just restarted it to begin with, sorry. There are 2 charts you want to familiarize yourself with. Let's see if I can rotate this. I'm going to post this on Piazza, so you'll have it too. So do you recognize all these acids? Actually, we went through more than these because we went through the other chart. This is more comprehensive. This chart's a little slimmed down, except for this. This chart's a little bit more comprehensive than this. The weakest acid we had on that chart was NH3, ammonia. The weakest acid we have on this chart is not ammonia. This acid's even weaker. The weakest acid on this chart is methane. Methane, CH4, is not really considered an acid. But if something were to come and pluck off that hydrogen, then we form this ion. This ion is extremely powerful base. This base is called methide. This base is very powerful too. You should know the name of this base, H-. It's called hydride, followed by oxide. Now you know the name of this one. What's the name of this one? Amide. This one you should know. Sulfide. And so all these are extremely powerful bases here. This is the cutoff. This ion is the cutoff, which is, what is this one? Hydroxide. So these bases are called the strong bases. These bases are called the weak bases up here. Like phosphate, carbonate. Oh, this one. Cyanide. Cyanide and hydrocyanic acid. Ammonia. Ammonia is a weak base. Monohydrogen phosphate, etc. You can go through the chart, read it yourself. All right, those are acid-base properties. The other properties that we want to know is something about electron poor and electron rich for redox. So, as far as redox goes, we have a chart like this. When you see a chart like this is pretty overwhelming, right?
Yeah.
Most people just look at it once and then say, forget it, it's too much, and never look at it again. But the thing is, everything looks overwhelming. In science, it's all overwhelming. What you do is you take it in little bits, as always. So, you know, initially when you collect a lot of data from experiments, it looks like this, a jumbled mess, and then you start going through it. First thing you do is just read through it, and so you register everything, like we did with that chart. That's what you do with every chart in science. From now on, with every chart in science, you should read every single entry, if you can. You know, some charts are just too big. That way, you'll start to, otherwise it is totally overwhelming, you know, and so you just take it little steps at a time, right? And so a lot of people never bother looking at a chart like this, but when you look at a chart like this and you look at it over time, there are a lot of patterns that you see in this chart, so you don't have to memorize anything. And so there are two types of people. There's a type of person who the only thing they can do is give me the chart, I'll look up the value. Right? If something does not occur on the chart, then they're out of luck because they have no idea how to deal with it. Versus the person who looks at this chart and then sees some patterns here. They see some patterns and then something appears not on the chart. Well, they can predict, you know, well, that's similar to this, so therefore I expect the properties to be like this. It's like on the acid side. On the acid side, you might have an acid like hydrocyanic acid that doesn't appear on that chart over there, but you can kind of guess, you know, it's got to be a weak acid. Maybe you can guess where it is. It's hard for acids. But here, you know, even though this looks pretty tough, there is definitely a pattern to this, and not just one, multiple patterns to this. And so what we're going to do is we're going to familiarize ourselves with this chart. Now, what does this chart help us to do? This chart helps us to understand what it means to be electron rich and what it means to be electron poor. What I said was about oxidizer and oxidizing. Remember, who does the oxidation? The oxidizer does the oxidation, right? And so if somebody does the oxidation, well, who are the good oxidizers? Can you name some of the good oxidizers? Oxygen. You know, oxygen is a great oxidizer, and the origin of the name oxidation comes from oxygen. Oxygen is plenty good to oxidize most metals. Take a look how much rust is out there, right? It's oxidation. But are there oxidizers better than oxygen? Well, here's a ranking. Here's oxygen here. Are there oxidizers better than oxygen? Yes, plenty of oxidizers even better than oxygen that could do the oxidation. What is the best oxidizer on the chart? Turns out the best oxidizer on the chart is at the top here. And what is it? Do you know the name of it? Okay, fluorine. Fluorine is the strongest oxidizer on the chart. So what does it mean to be a strong oxidizer? What it means to be a strong oxidizer is it means it wants electrons. Oxidizers want to take electrons. And so fluorine wants the electrons the most. How many electrons does it want? It just wants one electron for fluorine atom to form fluoride. So fluorine's an extremely powerful oxidizer. You know, so for example, oxygen here. If you have a piece of paper, this piece of paper is in oxygen in this room, you know, and is it combusting? Is it oxidizing? Yeah, very slowly. Have you ever looked at very old paper? When you look at very old paper, it looks charred, doesn't it? Because it's just combusting extremely slow. But if you have fluorine, this will ignite. No match needed. You just put this in fluorine, boom, you got a flame. Oh, okay, sorry. Stop here.